Well, hello there. It is I, Dr. Wisby. It is Friday night, and we are going to continue with chapter 3. If you're like me, then you're thinking about physics on a Friday night, and that's okay, because honestly, there's a lot worse things that you could be doing. But let's get started. So this will be part 2 of chapter 3. Last time we left in a very precarious situation. We were just on the verge of beginning to actually use vectors, and some people might say, why did you stop there? Well, sometimes things in life happen and you have to go. But now we have time. Oh, shoot. Never mind what that was. Okay. Oh, man. Okay. Well, anyways, thanks for watching. Let's get started. Okay. So we've got vectors and scalars. Vectors are always an arrow and a direction. Okay. The length of the arrow can't be negative because that's the magnitude of the vector. Okay. But if a vector is negative, that means it's pointing in the right direction. Somebody put something in the help and they said, how can you have a negative acceleration? What does that mean exactly? Well, mostly it has to do with the direction of the acceleration. Okay. So if, for example, you are slowing down in your car, you step on the brakes, your velocity is going to be in the opposite direction as your acceleration because you're stepping on the brakes. If your acceleration was in the same direction of you, you're going to be speeding up. So that'd be like you're stepping on the gas pedal. We don't want to do that. So let me draw a picture here. All right, so here's my car. Okay. And maybe maybe an electric Mustang. The electric cars are cool. They're so cool because you don't have to pay like $5 a gallon. Okay. You weren't seduced by the fancy spoilers and got a car that can only take premium, and now you pay $5 a gallon. I mean, oh, okay. But if you had an electric car, if you had an electric car, man, you wouldn't have to pay for gas. Yes, you'd have to pay for electricity, okay? But we can just burn natural. We have almost a seemingly infinite amount of natural gas in the US, okay? And so we could burn natural gas. We could use nuclear fuel rods and nuclear reactors to make electricity, no carbon dioxide pollution. Okay? And then we could charge our cars, maybe use solar panels. I mean, it's not hard, okay? You don't You don't need to pay $5 a gallon. That's only because we want to use it. We want to use gas, okay? Why? Well, I guess people like paying more money for gas. That's cool. You can spend your money on gas, that's fine. Okay, but my car here was driving this way, and if I step on the brakes, okay, if this way is positive, hey, if this is X hat here, okay, my velocity is positive. But when I step on the brakes, man, my acceleration is going that way. It better be going that way because uh it uh otherwise you're going to be speeding up, okay? If we think about another case, right, where your acceleration is going this way, right? Maybe your acceleration is this way. You're going to be going faster, okay? Yeah, so you'll be speeding up, okay? And maybe our car has doors like a DeLorean and Back to the Future, right? Did you see Back to the Future 2? They went to the future in 2015 and they had hoverboards, okay? Well, guess what? In 2015, okay, I was really disappointed because sadly there were no hoverboards, okay? But yet, yeah, there were no hoverboards. That was huge letdown. If you don't know what I'm talking about, watch Back to the Future too, okay? So now, but if let's say my car was going the other way, let's call this the negative X direction, okay? Then if I slow down, my acceleration's going to be in the positive direction. Okay, so if I wrote down the equation of motion for that, okay, how far am I going to travel? Okay, this would be x final equals x initial plus v. Oh no, this would be negative because we're going the other way, right? This would be v initial t. Okay, and then over here, let's see. Yeah, this would be positive 1/2 at squared. Okay. Well, I'll tell you a little story about this equation. So one time when I was younger, my dad had rented a Mustang. I was like, "Oh, this is so cool!" And I had my driver's license. I think. And I don't know. You know what? I was driving the car. I don't remember, but I was driving the car. I was like, "Man, I'm gonna see what this thing can do." And so I went to the mall parking lot. And I was like, "Yeah, we're we're." We're gonna really go as fast as I can. And so I got in the Mustang, I stepped on the gas, and I started accelerating. I was like, oh my gosh, this is amazing. It was like, oh, it's so fast. And then I looked out the window. I mean, I was looking out the window, but I realized like I was running out of parking lot really quickly. I mean, like I had been accelerating across this parking lot and I was about out of parking lot. And so what did I do? Of course, I slammed on the brakes. And no one was there. I think I had my license, but I it started to slide and I slid and it went up over the curb and into like a grassy hill. So the car was fine. I was fine that time. But okay, my acceleration was not enough. Okay, it was not. It was not enough in that case to slow me down. So let's do a little yeah, let's make some approximations. Like when the grass was growing, right? Calculate the velocity of the grass. That was a great question because there are no numbers. I mean, how would you even think of that? I don't know. Still, it's hard to wrap your mind around that. But let's go back to the situation of me in the Mustang. Okay. And I'm pretty sure I hit about 80 miles an hour in the parking lot. And so, of course, we know that that was 40 meters per second. I feel like I was probably going more like 43 miles per second. Yeah. 43 meters per second, not miles per second. And I think that when I realized that the parking lot was running out, I had about 300 meters. Let's go with that. Okay. Yeah, I mean 300 it was definitely less than a kilometer and so I feel like, it was 300 meters. So we'll call my initial position actually, we'll call that 0. And we'll say my final position, well, we'll say no, actually, yeah, we're gonna find out how long it took me to stop. And I think that over here, here's my Mustang. Okay, drawing this, not this kind of Mustang. It kind of reminded me. Okay, we'll say that this was 300 meters. And so the question is, um, can I stop or am I gonna hit the curb? Okay, well, I already told you what happened. I hit the curb. Um, what is a reasonable amount of braking in a car? I feel like that if I were decelerating at 10 meters per second, that would be the force due to gravity. Okay. And I think that your car would definitely start to slide. And there's no way that my acceleration was 10 meters per second when I slammed on the brakes. So let's go with 8 meters per second. I slammed on the brake, but we'll go with minus 8 meters per second. We could go with 1G. Let's go with 1G. Sure. Let's do that. Okay. So my acceleration is minus 10 meters per second or 1G. All right. So that was my 1 meter per second squared. That was my deceleration. I was traveling at 40 meters per second, and oh man, I can already tell I'm gonna. But. Yeah, okay. Well, I don't know the time. Oh, this is an interesting question now. Okay, I don't know the time, but we can figure out the time. So, we want to say that F, then my final velocity equals 0, and my initial velocity here equals minus AT. Okay, we're going to solve to see how long it took me to come to a stop. Okay, and my initial velocity, I was definitely going at 80 miles an hour. I remember thinking, wow, this is amazing. Yeah, so I'm gonna move this over here. Uh, it'll become negative, so we'll have yeah, this is 40 meters per second. 40 meters per second, and my deceleration is 10 meters per second squared times t. Okay, so that gives me 4 seconds to stop, right? Yeah, 4 seconds. Maybe. Am I gonna That's not bad. Okay. Now how far is it going to take me to stop? Let's call my initial when I step on the brakes. Okay. Let's call that x equals 0. Yeah, we'll call it x equals 0. Now we're supposed to be doing vectors, but somehow I got into the story about the time that I was driving in a Mustang, probably with a license. I don't remember how old I was. Yeah. Yeah, that's the license thing that doesn't matter. Um, let's uh let's get back to the problem. Okay, so my initial is 0. We're gonna solve for x. Okay, so let's put in our numbers here. So x final then equals vi, and my initial velocity is 40 meters per second. Okay, times t, right? And my t is that was 4 seconds. We calculated that 4 seconds. Okay, that's how long it took me to stop. Because once my wheels locked, and they definitely locked because I started sliding, and this is minus here. This is 10 times 4 squared. Okay, we can put that in here now. Okay, so 4 times 40, that's 160 meters plus 4 times 4, that's another 160. Okay, so this is 160. Yeah, this is 4 times 4, 16 times 160. And let's see. Okay, so divided by 2, that gives me 80. Okay, so then that is 160 plus 80. So that gives me, let's see, 240 meters. Okay, well. Did I get 240 meters? Okay, well, in real life, I hit the curb, so I think the curb was closer. I was actually probably like 150 meters maybe from the curb. I don't know, but I went over the curve into the grass. Everybody was fine. The rental car didn't have any damage. No one even knew. I don't think my dad ever found out. But yeah, don't do that. Don't test the speed of your car. That's a bad a bad idea. Okay, but oh, that's why we were talking about negative vector. So negative acceleration, okay? Negative acceleration is opposite to your velocity. So if you're traveling down the road and you have a positive velocity, you step on the brakes, your acceleration is negative, and so that should you should stop. Okay? All right. So let's continue on here with the lesson. Okay, so we're gonna do some vector math now. All right. Two vectors are equal if they have the same magnitude and direction. Okay, so if they're pointing in the same way and they have an equal length, then the two vectors are identical. Okay, that makes sense. Yeah, that's not earth shattering. Okay, the next C is the net displacement because it describes the net result of the hiker having first a displacement of A and then a displacement of B. Okay, so if you were out in the wilderness and you hiked in a certain direction, um, so here, if you went along A, okay, we're calling A east. So you hike 4 miles east and then 3 miles north. Okay, where are you relative to your starting position? Okay, how far did you go? Um, so just like now, yeah. So that's the question. How do we figure out how much we how far did we get from the end? Now, these two vectors are at a right angle, it looks like, so that's easy. We can just use the Pythagorean theorem. Sometimes they're not at the right angle, and that's a little bit more complicated, okay? But here's some basic facts about vectors, okay? If you add two vectors together, then you could make another vector that equals those two. For example, here we go east 4 miles, and then we went north 3, so C is the distance between those two. Okay, and it doesn't matter if you do A plus B or B plus A. It's called commutative, which means that it doesn't matter which thing you do first. Now you might be saying, like me, okay, I understand commutative processes. Okay, I get it, man. I can go east and then north. Okay, or I could have gone north and then east. Huh? Yeah, that's you could do that. Okay, but one time I was in linear algebra and I was like, okay, but what is a process that is not commutative? Okay. And this kind of blew my mind. So I was like, I don't believe that there's such a thing. I don't know why I thought that. I was like, you know what? I don't believe in a non-commutative process. That's not a thing. Everything is commutative. And he's like, oh yeah? Well, he was a really funny guy. He's really quiet and he just kind of look at you like this. And he's like, oh yeah? Well, what if you put on your shoes first and then your socks? I was like, oh my gosh, that doesn't commute. I was like, you can't put on your shoes and then your socks. It's different. It's like, oh my gosh, there are things in this universe that do not commute, okay? Same thing. You can't put on your clothes and then your underwear. That does not commute. Don't do that and go to class or go on a date. No, don't do that. Okay. Non-commutative processes we discussed too. We need to talk about it anymore. Okay, but vectors do commute. They do. All right, so the figure shows tip to tail vector rule or the parallelogram rule. Okay. Tip to tail is easy. You just take vector D and put it at the end of E, and then that equals D plus E. The parallelogram rule is a little bit more abstract. Find the diagonal of the parallelogram, okay, and then that forms a surface, it forms, uh, find the diagonal of the parallelogram formed by D and E. Now is a good time to go to the PhET simulation, Okay. This is what we want. All right. I can make two vectors here. You can make them too by clicking on that link, and you should. I highly encourage you to. And then you know what? I'm going to make a sum. Yes. The two vectors will be added thusly. Aha. Okay, I guess I have to click on this. All right, so I'm going to I'm going to make my vectors each 10. No, this one's 15. Okay. We shall make them 10. Okay. I can put I can put it like this, and this is the X component or the Y component. So this would be my parallelogram. Okay. I can bend this one if I want to. Okay. I can do the parallelogram rule. Okay. Look at that. Okay. Now, um, these two vectors, A and C, form a parallelogram. I don't know why I got C instead of B, but that's okay. Now, if I take this vector over here, okay, and I put it here, oh my gosh, tip to tail. If I add A plus B, okay, then you put them together and it goes from tip to tail. You get this vector S, which is the sum of the two vectors. Okay. Uh, so that's pretty straightforward. Okay, just think of arrows, right? We're gonna mostly do it in 2D. You could do it in 3D. We're not gonna do that in this class, but the algebra gets a little crazy. I'm not gonna lie. Okay, we're gonna stick to 2D because uh, I think anybody likes to do like a lot of algebra. It's like some algebra is okay. I get it, man. Okay, I know everybody likes to do a little algebra. Nobody likes to spend like 10 hours, okay? I don't know. Algebra's not my favorite. Okay? Math was really fun when you get to calculus and you're like, oh, I get it now. Okay. There's actually a reason why you do all this algebra. Man, it was kind of boring before calculus. The algebra's really no, I didn't say it. I said it. It's kind of boring. So make your life easy. Stick to two dimensions. Okay. I always say, is this a physics class or is it an algebra class? I think it's physics. Just saying. Okay, so we got this cool video game here. I mean, it's a simulation, but it's not. I don't know if you want to call it a physics video game. It's fun though. Okay, you can make these vectors however you want to. Look at this! Boom! Hey, look, and if I make a negative, what does it do? Okay, how long is my vector here? Okay. It's a diagonal of two squares. I'm going to make a negative. Boom! See what I did there? I reversed it. I reversed it. That's what happens. If you make a vector negative, are you ready? Okay, watch my screen. I pay careful attention. Boom! He's negative. Wait, did I? No, I didn't do that right. Oh, there it is. Okay. C was it was to the right 3 and it was up 1. Boom! There it is. Positive, negative, positive, negative. Hey, it reverses it. All right, let's go back to the presentation. I hope that the presentation helps you. I want to go through this stuff so you get it. I know a lot of people haven't ever taken physics before. Okay. All right. Given the vectors P and Q, what is P plus Q? All right. Well, let's go to the app, man. You know what? We can just do it. We don't have to imagine it. I mean, you should imagine it. Okay. Now let's see here. What did P and Q even look like? Okay, P is down and to the right at a 45-degree angles, and Q is to the left. Dang, I want to see the answer. Okay, so we'll call it. There we go. That is P, and this is Q. Okay, right there, man. Okay. No, What? Is that what P and Q look like? Yes, it is. I think P may be slightly. I didn't draw. I think they're about the same length. Yeah. Okay. It's more like that. Yeah, that. It's more like that. So, okay. I think. Well, I can clearly see here, right? I'm just gonna put them end to end. That's the easiest thing to do. If you have these two vectors, put them end to end, right? I know the parallelogram thing, yeah, it's true. Is it useful? Not really. Who thinks about parallelograms? But the tip to tail thing, that makes sense. I can do that. Okay. Just take one vector, put it on the end. You can even do it on paper. Get a scissors. Do you have a scissors? You can draw little arrows on paper and then you can cut them out. Yeah, you can. Let's make little cutouts of the vectors. The video game is nice. I like the video game, but I like paper too. Okay, so we're gonna actually make some cutouts of vectors. We're gonna craft some vectors. Um, P. Oh man, I don't. What the heck? All right. So we have a vector going this way. We'll call this one P. And then we had one going down here, Q. Okay. Well, let me go grab a scissors. We're gonna make some cutouts. It's I got my scissors here. Now my vector. They're really just little arrows, right? And I can actually, you can shoot. Did I? Oh, man, seriously? Okay, well, don't cut off the end. Man, you know what? That's okay because that's why we have Scotch tape. Yeah. Where did my tape go? Haha! There's my tape. See, everybody laughing. They're like, "What do you need tape for?" I knew I needed it. But this moment in time, this is why I needed the tape, actually. Yeah. You can heal a vector with tape. There we go. We have a vector. Ah, cat is Zeus, you're not helpful right now, okay? Zeus, look what you did, man. Oh, Zeus. You messed me up. He's I thought we talked about this, man. Okay? When I'm making vectors, you can't like be bumping my arm. I'll get you some food, okay? Jeez. Okay. I got my two vectors here, P and Q. Okay, so I'm gonna make it like this. I think Q was going down to the right here. Yes, there was Q. And so we can draw a vector from the end of this one over to there. So resultant vector is kind of down and to the left. All right. And let's see. Let's pick our answer here. All right. So I think the answer is A. Yes, the answer is A. We basically, oh, yeah, we got the right answer. No, we didn't. I drew it backwards. What? Well, okay. Let's make it again. All right, so we had one going to the left. Q is going to the left. There we go. And then P is going down to the right. You know what? It didn't matter. It made the same vector. I guess the universe is trying to tell us something. All right, multiplying a vector by a positive scalar is another vector of different magnitude. Okay, if you multiply by a scalar, it is It just makes the vector longer. It doesn't change the direction. So if you multiply it by a scalar, you're just increasing the magnitude of the vector. Okay. If we multiply by a uh, vector by zero, the product of a vector having zero length, the vector is known as the zero vector, which we'll never use in this class, but okay. The magnitude of a vector can never be negative. If the vector becomes negative, that means it just points in the negative direction. So it changes the direction and makes it opposite to what it was. Okay? So here's A. We multiply it by 2, that makes it twice as long. Then we multiply it by a negative 3a, that changes the directions. Okay. We got to pick it up a little bit. We're taking too long. Which of the vectors in the second row shows A plus B? All right, well, basically they go tip to tail, so I'm going to move B down over here, and then that would be a vector that comes out here. So I guess the parallelogram method makes sense for this one. I think the answer is C, because it should go out here just basically uh, it'll be an arrow that looks something like this, and the only one that, because the y components of a and b cancel each other out, and so we only have the x component that adds, and so the answer is definitely C. Gotta be C. All right. To subtract b from a, draw a, okay, and then place b there, place the tail of negative b at the tip of a, okay, b's right here. It just flipped the direction. Okay. So then we draw a vector from A to B, and that is A minus B. That's our new vector. So we just connect these right here. Okay. So you drew your vector. Okay. Then you're just going to draw your arrow right there. That's A minus B. Okay. Uh, oh, my purple vectors are staying there. All right. Given vectors P and Q, what is P minus Q? Okay, Q is going to be flipped around here. And no, what the? What do you want, Zeus? I already gave you a snack. My cat is back. Okay, I'm going to go Control Z, Control Z. Oh, delete that. All right. So we're gonna reverse Q, okay? And I'm gonna draw another Q here. Gonna start right here and it's gonna go this way. That's about the right length. Okay, and then P minus Q is gonna go from the end of big P to the end of Q over here. Okay, so just think of vectors as arrows that you're connecting the ends to end. You can add the x component to the x component of one and the y component to the y component. Okay, so the correct answer is D. I've got my vector and I can move it down here. Wait, what? No, there it is. Okay, I wanted this. There we go. All right, so yeah, I was P minus Q. That's about right. Okay, delete my vectors, and we're gonna go on. Okay, we're getting close to the end. Friday night. Which of the vectors in the second row shows 2a minus b? Okay, so here is a. Okay, so we're gonna double a. Okay, we're gonna double a. I'm gonna go bloop. There's a, and then I'm gonna draw a negative b. Oh my gosh. Okay, and then the resultant vector. Okay, what am I gonna do? Oh, I'm gonna move. Okay, see, this is cool because I can move my vector over here. Boom. Tip to tail, baby. The change of color, I'm gonna do purple. I like purple vectors. That's true. I do like purple vectors. I don't know why. There's my answer. It's pointing that way. Now, why don't any of the pictures look like that? 2a minus b. Okay. How's my I swear I drew right. I don't know why this thing's giving me a hard time. All right. Here's my vector. Oh, it's A. The answer is A. Jeez, man. I moved my vector. I couldn't see it. Okay. I couldn't see. I saw the purple vector. I even drew it myself, and I was looking at B. I was like, does it look like B? Well, it's because it's A. That's why A does not look like B. Okay, let's talk about the coordinate system. Okay, we're gonna go on here for a couple minutes. We're gonna try and make some progress. Okay, coordinate system and vector components. Okay, each vector has an x and y component. Okay, in our coordinate system, we've already done. We've already done a little bit with coordinate systems. We drew it. We're saying x is to the right and it's positive. Okay, and y is up, and they're 90 degrees apart from each other. We call these Cartesian coordinates. Any vector has a component in A or B. Okay, so here's A. We have an x component and a y component. Okay, and so we could also write, this is really important here. Okay, this, let me circle this because this is extremely important. Okay, I'm gonna circle this part right here. This is how you can break down a vector into its components, right? We could rewrite A as an x component and a y component. And if we add it to another vector, then we just add the x component to the x component and the y component to the y component. That gives us our new vector, okay? And x and y are always perpendicular to each other. And so then if you want to find the magnitude, you just use the Pythagorean theorem. Okay? So let's go on here. I feel like we should talk about that. Okay. Let's yeah. Let's do an example. Okay. Here we go. I'm gonna draw here. Webcam out. Okay. So we're gonna make up an imaginary vector. Okay. Make number line over here. Give it some numbers. 1, 2, 4, 5, 6, 4, 5. Okay. So my vector is going to have x components that go over here. So we'll have x component here. This is one of my vectors. And then we'll have our y component over here. Okay. That's our y component. And then we're going to draw our vector. Okay. Tip of this one. Okay. And I'm gonna make my vector purple because, as I mentioned, I like purple vectors. I don't know why I like purple vectors. Okay, so here is our vector. It is purple, and it's right there. But what is the magnitude of our vector, and what's its direction? All right, well, let's write down the x components here. So the x components, well, this is going to be x in meters, and this is going to be y in meters. Okay, my x component is going to be ax. X is going to equal 1, 2, 3, 4, 5. Okay. So 5, and then I'll write x hat here. Okay. And then this is my vector A. That's my vector A. Okay, then we're gonna have in pink over here, this will be AY, the Y component of my vector is gonna be 1, 2, 3, 4. Okay, so 4 times y hat. And this y hat, okay, I keep talking about x hat and y hat. Okay, x hat is a vector that has a length of 1 and it points along the x direction. This is x hat, okay? Unit length 1. Okay, I'm going to draw y hat over here too, just so you guys can get a picture of it, okay? This is y hat. It's a vector that has 1 unit length, okay? It's dimensionless, okay, and it just points along the y-axis. And we know here that here's my vector yeah, 4y, okay? And I'm going to add this to another vector. Well, because we'll do the whole thing here, and then after that we're gonna stop. Okay. My other vector, oh my dear, turquoise. Okay. My other vector is gonna be, we'll draw it like this. Okay, so here's my vector B. Okay, that's my vector B. What are the components of B? Okay, well, B is right here, and it's right there. You thought I was gonna go right there? No, I didn't. I tricked you. I ended up right there. All right, this is B. So BX hat is right here. Okay. BX hat right there. And then or B, yeah. And then let's see. Yeah, here's the Y component of B. Okay. So we're gonna write down the vectors A and B, and we're gonna add them together. Okay, and then we're gonna draw the resultant vector on here. Okay, and then I think I'm probably gonna go to bed because it's gonna be midnight then. All right. So B A, let's draw the vector A. Okay. A, my vector A, okay, I'm writing the whole thing out in its full glory. Okay, we've got yeah, we got 5x hat here plus 4 y hat. That is A. And then vector B is going to equal, and then what is that? That's 2.3, no, about 2.4. I'm pretty sure it's 2.4. How can I be so precise? It's because I'm a physicist. No, it looks like 2.4. I don't know. Okay. I'm trying to be serious because physics is very, very serious. 5 y hat. I mean, if it's all just serious all the time, it's like, that's no fun, is it? No, that's no fun. All right, so we got our vectors here, okay? And we're gonna add A and B together. Yeah, let's just do it. And then we're gonna draw the resultant vector. All right. Hmm. Righty. Let's just do A plus B here. So we're gonna write the vector A plus B. Okay, so I'm just gonna write A first. Okay, A is, yeah. So we'll write down the components here. So we have 5x hat plus 4y hat, and then we're going to add these together. So this will be 2.4 x hat plus 5y hat. Okay, so now we just add the components together. Okay, so, and I'm going to call this D, vector D. Okay, it's just going to be D. I can call whatever I want to. Okay, so my x component of D then is going to be 7.4 x hat, and then I add the y components together. That's going to be plus 9 y hat. Okay, so I got my new vector. I got A plus B, so I'm going to draw it. I'm going to draw it now. So D goes to, let's see. This is 5, 6, 7, 7.4, so it's right here. And then the height is 9, so it's 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. I didn't, okay, there's 8. Okay, so it's gonna go up here and it'll go all the way to here. Okay, so my resultant vector D goes all the way up here. Goes up there. There's D. Okay, because down here this is 7.4 up there. And then up here, that is, zoom out a little bit. Okay. And then up here, this is 9. Okay. So I got my vector here, but what's the angle of D, and what's the magnitude of D? That's what we need to know. All right, and so I'm going to say, what's my angle here of D? Okay, well, since this is a right triangle, okay, over here, this is a right triangle, I can just use trigonometry to get this. I'll find the magnitude of D first. So here's D. I'm going to put it in these two brackets. And when I do that, what it really is doing is it's basically D dot D. This is vector multiplication. You multiply two vectors, you multiply the x components together and the y components together. Okay. And I'm going to take the square root of this. Okay. And so what do I get here? Well, D is 7.4 times 7.4. Okay, so I'll write it out in all the steps. 7.4x plus 9 y hat, and I'm going to dot this together. When I do the dot product of two vectors, okay, when you do the dot product, you multiply the x and y components together. And here's the reason why, okay, because if you say x hat dot x hat, okay, so I take these two vectors um, up here, my x hat, this equals 1. The magnitude of this is 1. Okay, but x and y hat are perpendicular. So if I say x dot y, that equals 0. So all my cross terms in here, they all just go to 0. And y dot y, I think I already did this once, equals 1. Same thing for z. Okay, if I had 3 dimensions, z dot z equals 1. Okay, so now when I multiply this, all my cross terms are 0. Okay, so I have 7.4 times 7.4. Okay, so that'll be 7.4 squared. And then I got plus, I multiply my 9 by 9. That's 9 squared. So this is like 52 about ish, I think. Because I know 7 times 7 is 49. What's 7.4? What is 7.4 squared? I think it's, what I say? 52, 7.4 squared. Nope, that was not the one. Dang it. Okay. 7.4 squared. Oh, just okay. My big sausage fingers can't push the buttons. 7.4 squared is what I say, 52. Oh, 54.76. Okay, that was close. You know what? It's fine. That was yeah, all right. That was close. It's the right order of magnitude. 54.76 plus 81. Okay, so I'm gonna say plus 81. The answer is 135. I'll take the square root of that. Okay, and the answer is 11.65 meters, or we could just round this up to 12. But I think I'll go with 11.7 because yeah, that's fine. But what's my angle? Okay, what is my angle right there? Okay, my angle theta is going to equal, okay, well, I know that tangent of theta will equal y over x, okay? And y is 9. Okay, so y is 9. This is 7.4. And, oh, my calculator fails me again. Does anyone know if the iPhone has arctangents? I mean, what the hell, Apple? Seriously, it would be such a great. You can't put arctangent on there? Seriously? I mean, you can pay wirelessly, right? I use Apple Pay. I tap to pay and they can't put freaking arctangent. I said freaking arctangent. Oh man. Okay, I'm gonna take the arctangent on both sides here. Yeah. We're gonna take arctangent on both sides. So I'm gonna say arctangent minus 1. That's my arctangent. It's gonna give me theta. And then I'm gonna have arctangent of 9 over 7.4. Okay, well, I can't do it on my phone, which is terribly disappointing every time I am reminded of Apple's failure. Okay, arctan D, that puts it in degrees because MATLAB you can't set it to degrees. It's either you just you just have to tell it D on the end and then it's in degrees. Okay, so our angle then of our new vector is 50.572. Okay. So theta equals 50.5722. Wonderful. Okay, so then the magnitude of my vector, okay, so you could write it as my vector D is equal to 11.7 meters at 50, we'll say 50.6 degrees north of east. All right, this is another way you can write a vector. Probably not the best way, but you can. And it is midnight. And so that brings us to the end of our video. Thank you. Thank you for watching. Um, well, this video should be online at possibly at 12:30 Saturday morning, 12:30 a.m. So there'll be more videos tomorrow. So look out for the rest of chapter 3. Chapter 4, hopefully we'll get to on Sunday. But send me your answers, send me your questions on the discussion board. There's a help discussion board, in case you were wondering. I do check it. I checked it today, and there was actually a question there. So thank you for posting that. Just a reminder, on your discussion board, click here, and there's discussion and help. And if you write me here, I will get back to you. Okay. You can also post it in Discord. Okay. Um so I'm gonna make a video of this one too. Number five, yeah, in chapter 3. I'll do that tomorrow. 5 in chapter 3. So look for that in the morning. You can join me for breakfast. Toast and physics. And maybe some coffee. Definitely coffee. Have a good night. Thank you, Bulbasaur.